All right, yeah, Thanksgiving is up upon us very soon here, last day of class before Thanksgiving. I will try to get us out, maybe even 10 minutes early, okay? So I'm going to try to go fast here. We do have important content to cover. I will be going fast. I got a lot of stuff to show you on the spreadsheet. You may prefer just focusing on what I say and seeing the not the spreadsheet, but the PowerPoint and downloading that out of class. Lecture 23A, we're going to focus on something in Chapter 9, which was not originally on the syllabus, but I decided it was important enough to cover. Two-way tables and the chi-squared test. Don't say chi, say chi, when you see chi. Then in Lecture 23B, we'll be going back to Chapter 10 again, the regression model. Talk about something new, regression standard error, and estimating the population slope and intercept with sample slope and intercept, focused on not formulas initially, but how to get the answers from the spreadsheet. All right, so Chapter 9. Chapter 9 is about what are called two-way tables, where essentially you have two categorical variables that you'd like to compare, and it's kind of analogous to regression. Though regression is with quantitative variables. You're looking at relationships between explanatory and response variables. Does one variable explain the other? Does one variable respond to the other? Same kind of thing here in Chapter 9, except it's with categorical variables. We'll consider an example in a minute. It's also got a relationship to Chapter 8 in that you can compute proportions of things. Though in Chapter 8 we focused on sort of a binomial setting, counting successes and failures and then converting those to proportions. In Chapter 9, you've really got more proportions going on, and it's more than just success or failure in general, though the book's main couple examples in the first parts of Chapter 9 do focus on situations where Chapter 8 methods would still be useful. Here's an example. Suppose we take a poll of adults and we want to determine their preferences for Friday night meals. The poll gives them three options. Do you want to eat home-cooked, takeout, or at a restaurant? As the three options for their preference for what they want to do on a Friday night. Okay, so it's not just success or failure. There are three options rather than just two options. That's one initial important difference between this and Chapter 8. And let's say we want to see if the responses differ between men and women. Okay? So you do have two categorical variables going on here. You've got the type of option for a Friday night meal. Meal option would be one categorical variable. Three different possibilities again, home cooked, takeout, or at a restaurant. And you've got another categorical variable, and that would be the sex of the person, man, male, or female. And we'd like to see if the responses differ. You might think, as a natural thing to do, that perhaps there are differences between men and women. Perhaps the person's sex is the explanatory variable, and what they want for dinner on a Friday night is the response variable. Here are the results, and we're putting these results in what's called a two-way table. It's important to understand what this table is telling you. Maybe start down here. You've got 33 people total. Very good. Total number of people that are surveyed. Of those 33 people, 16 are men and 17 are women. Also, of those 33 people, the overall responses, if you don't take male or female into account, is that 12 out of 33 want home-cooked, 10 out of 33 want takeout, and 11 out of 33 want restaurant. But then, based on the fact that we kept track of whether we were talking to a male or a female here, we can also break it down in terms of males and females. 8 out of 16 males want home-cooked, 50% of them. That could be converted to that proportion. 8 out of 16 would be 1/2 or 50%. 3 out of 16 want takeout, 5 out of 16 want restaurants. For the women, it's 4 out of 17 who want home cooked, 7 out of 17 who want takeout, and 6 out of 17 who want restaurant. If you add the numbers in these columns, 8 plus 3 plus 5, you do get 16. Also 4 plus 7 plus 6 gives 17. 12 plus 10 plus 11 gives 33. Conversely, going across the rows, 8 plus 4 equals 12, 3 plus 7 equals 10, 5 plus 6 equals 11, and 16 plus 17 equals 33. And so in fact, what would typically happen is you would not necessarily be given the totals. You might only be given the numbers that are in the blue regions here, the blue boxes or blue cells, and you'd have to figure out the totals. Okay? That would be typically what you would be given, and you would have to figure out those totals. But anyway, this is a two-way table. And again, we're wondering whether the person's sex, male or female, determines or influences or explains their responses about the preference for what they want to do on a Friday night. And for one thing, we can observe that for this sample, men are twice as likely to want home cooked, and women are more than twice as likely to want takeout. You can think of it in terms of probabilities if you like. For this particular sample, the probability that a male wants home cooked is 8/16, 1/2. And the probability that a woman wants home cooked is 4/17, a little less than 25%. So I could have said they're even more than twice as likely to want home cooked. Women are more than twice as likely to want takeout, 7 out of 17 compared to 3 out of 16. You can think of those in terms of probabilities. We do see differences between the men and the women here. But as always with inference, the question is are those differences statistically significant or not? To say that for the wider population of males and females, that there are differences. That's the question. So we set up hypothesis test in chapter 9, but the nature of the hypothesis test here is different than usual. Okay? We're going to describe it more in words rather than equations. To do a statistical test in this context, to see if the differences between the men and the women really is significant, and not just by chance, we need some additional pieces. We need a null hypothesis. Here's the way the null hypothesis goes. Notice, just like I said 30 seconds ago, there's no equation there. It's a description. The null hypothesis is that there's no difference. There's no difference between men and women as far as their meal preferences on Friday night. You give the null hypothesis, as always, the benefit of the doubt when you do the test. You assume it's true, and you look at the statistical evidence, assumed to come from a simple random sample, and say, does this evidence provide statistically significant evidence against the null? Is the p-value real small or not? The p-value is a measure of the probability of observing your data, your sample data, your statistical test, your test statistics, as extreme or more extreme as what you actually observed when the null hypothesis is true. It's always the same kind of idea with the p-value. The way you calculate it is different, but the basic idea of the p-value is measuring that chance of seeing data as extreme or more extreme as what you actually observed when the null is assumed to be true. That stays consistent through all kinds of tests. The alternative hypothesis is not going to be right-tailed or left-tailed, or two-tailed, although it is a little closer to two-tailed actually, as we will see. But we're describing this in words. There is a difference between the sexes as far as their meal preferences on Friday night. Okay? There is a difference. That's the alternative. The distributions of preferences for home-cooked versus takeout versus restaurant for the population is different. That's the assumption in the alternative hypothesis. We don't worry about one-tailed versus two-tailed, though there is a relationship to two-tailed tests for simpler examples than the one we're doing. Here's the big question, though. What's a meaningful test statistic? Is it Z? T? Well, it's neither of those. It's called chi-square. Kind of a strange name, but that's what it's called. In the past, to calculate the test statistic, we often used the value of the null hypothesis. Right? Whether we were calculating Z or T, we were computing x bar or p hat, a mean or a proportion, and then using that, we were subtracting the null value typically, and then dividing by a standard error. We use the null value to check the likelihood of the measured statistic value that we get. But we don't really have a value here. What's the null value? There is no number in that null hypothesis. So this is kind of a mystery that we trust the statisticians to solve, and we'll see how they solve it here in a few minutes. Got that? You got the big picture here? And this is an important point. You should know that this is the way the null hypothesis and this is the way the alternative hypothesis are phrased in this context. Okay, for this example. For another example, you'd have to modify it, but basically, again, the null hypothesis is there's no difference. There's no difference in the distribution of the response variables, in this case, the type of meal they want, related to the explanatory variables, in that case, the person's sex. So the explanatory variable goes up here. I'm trying to write explanatory, but having a hard time here. Explanatory variable, in this case, the person's sex. And the response variable, in this case, their Friday night meal preference. And just like with x and y in regression, x goes horizontal, y goes vertical, the same thing is happening here. The explanatory variable goes across the top, and the response variable goes up and down. Okay? Just like x is horizontal and y is vertical. That's the traditional way to do it. If eating preferences are really independent of sex, then, for example, the proportion of men who want to eat home-cooked should be the same as the proportion of all the adults in the survey who prefer to eat home-cooked. Okay? In the idealized situation where the null is true and moreover the sample data truly reflect the population, you would expect the proportion of men who want to eat home-cooked to be the same as the proportion of all adults, males and females, who prefer to eat home-cooked. What's the proportion of all the adults in the survey who want to eat home-cooked? 12 out of 33. A little more than 1/3. In reality, 8 out of 16, 50% of the men wanted home-cooked. Where again, for all the adults, it was just a little bit bigger than 1/3. Let's look at some details of some calculations. Again, for the men, for overall, 12 out of 33 prefer home-cooked. Again, that would be a little bit more than 1/3. So, since there's 16 men, look at this calculation here. You might want to double check it with your calculator. Since there's 16 men, if you took the number of men times the proportion of all adults who want to eat home-cooked on a Friday night, you get 5.818. That would be the expected number of men who would prefer home-cooked out of 16 if the proportion of men who wanted home-cooked on Friday night matched the combined group proportion, 12 out of 33. Now, of course, you can't have 5.818 men. It's got to be a whole number, 3, 4, 5, 6, 7, 8 out of 16. But we go ahead and we work with the decimals anyway. Okay? I'm actually going to round a little too soon in this, which goes against what I usually do. But for the sake of clarity and not seeing too many numbers, I will be rounding initially, though that could lead to errors later on. I'm going to go ahead and round that to 5.818. It does keep going. It's a repeating decimal. 5.818181818, etc. I'll go ahead and round it just for the sake of clarity to keep the numbers shorter in what you see here. Similarly, for the women, if you focus on eating at a restaurant, overall 11 out of 33 of the adults, exactly 1/3, want to eat out at a restaurant on a Friday night. For the women, it was 6 out of 17, which is a little higher than 1/3. Since there are 17 women, if you take 17 times 11 over 33, which is again the proportion of the adults overall who want to eat out at a restaurant, you get 5.667. That would be the expected number of women who would want to eat out at a restaurant on a Friday night if that proportion matched the true overall population proportion for all the adults. Notice that for the men in the home cook, 5.818 is not super close to 8. It's not 7 or 9, for example. Whereas 5.667 is pretty close to 6. So the fact that this number is further away from that, whereas this number is closer to that, this number is going to provide more evidence against the null hypothesis than this number will, is what I'm trying to say. Say that again. This number is a little further away from that than this one is from that. So this number, compared to this number, is going to provide more evidence against the null hypothesis that the population proportions for males and females is the same, compared to this number. This number is not going to provide much evidence against the null, because it's well, these two numbers are fairly close to each other. 6 out of 17 is pretty close to 1/3. 11 out of 33 is exactly 1/3. So that's a little intuition. You want to take this and now form a table of expected numbers. Here's the original table. I'm calling that the actual table. Here's the expected table when you assume the null is true. And again, when these differences between the corresponding values in these cells is relatively large, that provides more evidence against the null, intuitively at least, than when the difference is small, though it's also relative to the size of the numbers themselves. So 8 minus 5.818 is 2.182. That is a bigger number than 6 minus 5.667, which is just 0.333. There's another fairly large difference between the 4 and the 6.182. That's going to provide more evidence against the null, etc. All these numbers in this expected table can be computed in the same way that I showed you in the last slide. For example, if we want to compute this one right here, 4.848, you can try this with your calculator. The overall proportion of males and females combined who prefer to eat takeout is 10 out of 33. And again, there's 16 males overall. This is in the male column there. You could calculate that number by taking the 16 males overall and multiplying times the ratio 10 out of 33. Go ahead and give that a try in your calculator right now. 16 times 10 over 33 should give you 4.848. I'll go ahead and try it too. Maybe you prefer to calculate the ratio first. 10 divided by 33. 30.3% of all the males and females surveyed preferred eating takeout on a Friday night. Multiply that times the number of males times 16, and you get the expected number of males who would want to take out if the null hypothesis was true, that the distribution of the men and women who want these different options on a Friday night match the distribution for the males and females combined. So you can certainly calculate those numbers in this way, and that turns out to be equivalent to the following formula. To find the expected count for each one of these cells in blue in this expected table, take the row total times the corresponding column total for that cell and divide by n, where n is the total number of people here. It's the 33 in this case. So for this particular number that goes right there, if you use this formula, you would take this table, you'd take the row total for the men who want takeout, which is 3 plus 7 is 10, times the column total for the men who want takeout, 8 plus 3 plus 5 is 16. Take 10 times 16 and divide by 33, which is what we did here, really. 16 times 10 33rds can be written as 16 times 10 over 33. This formula gets you the right answer. It does kind of disguise the fact that in reality you're trying to take these proportions, like the 10 out of 33, and multiply 10 times the total number of, in this case, males, to get the expected number of males you want to take out. This formula kind of hides that fact, but it does give you the same answer. And it's, without thinking, it's kind of just an automatic way to calculate these numbers as quick as possible. That's the point. But you shouldn't forget about the fact that in reality, the logic is important too. It's coming from, again, taking the actual proportion of males and females combined who want to take out on a Friday night, 10 out of 33, and in this case multiplying times the number of males to get the expected number of males who would want to take out if the null hypothesis was true. You shouldn't forget that logic. But this formula is just a quick way to get this table without thinking about that. It does give you the same answers. Try it for another one. Check this number right here, 5.333. That's in the male column in the restaurant row. So take 16 times 11, divide by 33. Give it a try. 16 times 11, divide by 33. You'll get 5.333. And then you can do it as a two-step process if you like. 16 times 11 is 176. Divide by 33. You get 5.3 repeat. Okay? That happens a lot in math where you have some formula that you can use without thinking about it just to do the calculation as fast as possible. But I don't want you to forget where that formula comes from in this case. Think about the logic of proportions. Once you've got those expected counts, you can calculate what's called the chi-square statistic. One reasonable thing you could do is you could look at those differences between the observed numbers and the expected numbers. Some of those differences will be positive, some will be negative. So to get rid of the negatives, you might want to square those distances and add those squares as we often do, like with standard deviations and with SSE. We often square differences, right? Differences of the squared residuals, and we add them up. Turns out to be a good idea, like I kind of hinted at a couple minutes ago, to take into account the size of the expected value. If it's big, then a big difference might not mean as much. If the difference between the observed and expected is fairly large, but the expected itself is kind of large, that's a small percentage change. So that large difference might not mean as much because of that. So you want to kind of standardize, you want to divide by the expected values. And here's the formula. That's not an x there. That's a chi. It looks like an x, of course. But we think of it as a Greek letter chi. It's being squared. You might scratch your head and say, why are we calling it chi squared? If I have time, I'll explain that later today. Otherwise, next week. You add up some ratios for the table for those blue cells. Just focus on the blue cells, don't focus on the totals. For each one of those blue cells, and there were 6 of them in each table, calculate this ratio, take the observed count minus the corresponding expected count, like for males who prefer restaurants, for example. Square that number, do it for each one of those cells. Divide by the corresponding expected count, and then add up the results. That's called the chi-square statistic. Just like t variables, it's going to have a certain number of degrees of freedom we will see. And the formula is going to be different. It's not n minus 1 here. Okay? Degrees of freedom depends on the context. I'm going to calculate this thing. This thing is typically kind of a pain to calculate. And the test, probably what I'd have you do is not have to calculate it completely, but write down the formula at least and maybe calculate one of the terms to show me that you know how to calculate one of the terms in the sum. And then I'd probably tell you the answer for what chi-squared equals at the end. You get what I'm trying to say? To save you some time, but at the same time illustrate that you understand the idea of the formula. I'd have you make you'd be given the actual table, you'd have to make the expected table. You'd have to maybe compute one of these ratios, and then I'd tell you the answer for the full summation after that point. Then you just have to know what to do with it, as we'll talk about here in a few minutes. For this particular example, well, okay, let me skip this part here. For this particular example, here's the value of chi-squared. It ends up being close to 3. Try to remember the table. Maybe I should try to redraw it on the board quick. You have the actual numbers. Men and women. You have the home cooked, takeout, and restaurant. It was 8, 4, 3 for the men, and 7, 5, 6 for the women. That look right? And this was 16, 17, this was 15, 9, 9. That doesn't seem right. Something wrong there. I better look. Yeah, okay, I'm writing these wrong. Where'd the eraser go? Eight and 4, 3 and 7, 5 and 6, 12, 10, 11 over here, and the total number of people is 33. The expected counts, I'll just put them in the same table. 5.88, 5.818, 6.182. These are not fractions. 4.848. I'm just trying to combine the two tables into one. 5.152. 5.333. And 5.667. Again, these are not fractions. Don't misinterpret that. I'm just trying to get these in the same table to save some time. What did I do? For each one of these cells that were colored blue in the middle here, there's 3 rows and 2 columns. There were 6 of those cells. I took the observed number, in this case 8, minus the expected number, 5.818, square that number, and then divide by the expected number for that cell. And then do that for the other 5 cells. You can check in your calculator, though it takes a bit of work, but this comes out close to 3. What's the degrees of freedom? It turns out to equal the number of rows minus 1 times the number of columns minus 1. In this case, that's 2 times 1 is 2 degrees of freedom. There are 3 rows for the meal preference, 3 choices. And there are 2 columns for the person's sex, men and women. The 3 corresponds to the number of meal choices. The 2 corresponds to the number of choices for the person's sex. 3 minus 1 times 2 minus 1 is 2. Now we use a table, a new table that you've never used before. It's called the chi-square table, as you might expect. Zoom in on this here. Based on 2 degrees of freedom, this says DF over there if you can't quite see it. This is in not the very back of the book, but in the near the back in the table section. It's table F. This says chi-square distribution of critical values. That says degrees of freedom. We're after 2 degrees of freedom. This says tail probability, and notice it's a right tail. That's what these numbers are, 0.25, 0.2, 0.15, 0.1, etc. Those represent areas. And these numbers represent points on the axis. Our point was close to 3, which is between these 2 numbers. Those 2 numbers are 2.77 and 3.22. Therefore, our p-value for this test is between those 2 numbers, 0.2 and 0.25. So that's a fairly small p-value, but not really small. Not less than 10%, not less than 5%. We've got some evidence against the null, but it's not real strong evidence against the null. For typical levels of significance here, for this p-value that's between 0.2 and 0.25, we would not reject the null hypothesis. We don't have really strong evidence against it. It's probably partially because the sample sizes are fairly small. If we had similar proportions with larger sample sizes, I bet we'd get a smaller p-value. Okay? We're going to go ahead and take our break to take our quiz, but I will talk briefly about this a little bit more before we get back to regression.